It's more like an experience report. So while working this year, when Pavel came to the lab, and we started working, we started looking at some problems with Pharo, particularly with memory leaks. And okay, we wanted to share what we found. What were the problems we had? How did we solve it? What were the tools we used? And so on. So that's kind of the story in short. So we wanted first to say that Smalltalk is a garbage collector language. We have a garbage collector. The garbage collector is there in charge of freeing objects. So it should free memory. So we shouldn't have, if there are objects that are not used anymore, they should be taken care of by the garbage collector. We shouldn't care about objects that are not used anymore. So many people think, first there are many different myths around garbage collectors, and many developers that are not so experienced, they think that garbage collectors are magical, and that they actually will take your objects when they are not used anymore. But that not used is the definition of what is used and what is not used is not so simple. So one thing that we want to avoid is to have people thinking that a garbage collector language avoids memory leaks. That's not true. Yeah? So there are memory leaks if you use a garbage collector language. I'm not saying nothing new. So and there are two main kinds of memory leaks you may find. One is the ones that you may find in your own application. You may have some objects that are not collected. So yeah, clear. If you have your user object and then if your user object is never taken, then the memory of that user object is never free from the memory. That is the memory that is managed by the virtual machine itself, whatever. And then there are other kind of objects that are what we say external objects. If you do a malloc on the C heap, so you are actually allocating memory that is outside of the control of the garbage collector. So you may be leaking sometimes memory from outside the environment. And if, for example, you are using FFI to create native windows, and if you don't free the windows, at some point your memory will explode. So you should take care of that. So, what is the base of garbage collection? So actually, I don't know, people say, yeah, an object is collected when the object is not used anymore. So to be a bit more precise, actually, in a Smalltalk image there is something that is called root objects. Yeah? So I draw them like that. So it's an object that has a root. That object will never be collected. It's an object that the VM knows, and the VM will say, that guy will stay forever, and I will not collect that guy. So if that guy knows some other objects, those objects that are known by the root objects, they will never be collected. So here, for example, the objects that are inside the red zone, they will not be collected. So how do we do? Sometimes we want to have some objects and we want to avoid some memory leaks. Okay, we have something that are called weak references. How many of you know what a weak reference is? Okay, 2/3. So I have one slide to explain what is a weak reference. So this is the same graph as before. We have a root object that knows two objects, and these two objects are not being collected. Okay, so a weak reference is a special kind of reference that actually the garbage collector will kind of ignore it. So if our root object has a weak reference to an object, then the guy that is only referenced by a weak reference will be collected here. And the other guy that is referenced by what we call a strong reference will not be collected. So that is in a really simplified way of saying. So what happens if we have external resources? Yeah, for example, if my object that was held by a weak reference has a file, has a reference to a file. Actually, I don't know if you know, but processes in the operating system, they have a limit on how many files they can open. So if we open too many files and we don't close them, at some point we cannot open any more files and we are dead. So if we are just leaving open files there, we have to close them at some point. And usually if the object that opened the file is collected, then we don't have the reference to the file in the operating system anymore and we cannot close it. So we have to take care of it. So all Smalltalks that I know, they implement something that is called finalization. So finalization, you can imagine it as somebody that is keeping special references that, and then the garbage collector will take a look at this finalization registry. So there's a registry of special references, and the garbage collector will take a look at them, and then we say, maybe I will garbage collect this object. So I will tell you before, so you can do some resource management. For example, before collecting the file object, I will tell you so you can close the file. Yeah. And in Pharo and Squeak, so far, we do that by, we register an object in the registry by saying weak registry default at an object. Yeah, we can create many different registries and so on, but this is the default way to do it. So, when we do that, once the garbage collector says, I will collect that guy. Yeah, so before collecting that guy, actually what I will do is send the finalized message to that guy, and when that guy receives the finalized message, he will close the file descriptor, and then we are not leaking files. Okay, this is in a really simplified way. Actually, the thing doesn't really happen like that, but this is what you need to understand so far. The thing is, okay, we have weak references that we can use to actually let the garbage collector to not hold our objects. We also have the finalization to close external references and external resources, but okay, sometimes it doesn't work. It's not magic. So, okay, I put this. The following images can affect sensitive people. Yes, because actually no matter how weak your references are, you may find memory leaks. Actually, sometimes people say, yeah, I am using weak references, and they think that their objects will go away. No. Actually, this story is motivated because we found memory leaks because people were actually using wrongly the weak references. So, okay, I have a story. I will read it because I wrote it. That's nice. So, once upon a time, there was announcements. So, people, you know the announcements framework? How many of you know it? Half of you. So it's a kind of observer library. So you have an announcer that is an observer. An announcer is a guy that is going to notify of some events to some guys that are registered to it. So then you can implement an observer mechanism using that. So we have announcements in Pharo. They're also in VisualWorks, if I am not mistaken. So it's an event delivery library. And then there was a princess that was called engineer that wanted to notify my object from an event. So the princess was saying something like that. Announcer when an event send message to my object. Yeah? Okay. So what happens if you do that, usually in Pharo? Well, what happens is that the announcer will hold a strong reference to my object. So my object, if I don't have any more references to it, the announcer will still keep it alive. So this is one source to create a memory leak, which is actually a bit strange because when you are using the announcer, the observer pattern, actually you want some loosely coupling. You don't want to actually couple myself to the guy that is observing me. So we want them to be independent. So okay, but this was causing a problem. So engineer, the princess, did love my object so much that it did not want to retain it forever alive. So it did not want announcer to hold my object strongly. So she wanted a weak announcer. And we have weak announcements in Pharo. A weak announcer creates a kind of a special registration to the announcer so that it will try to keep the object in a weak reference. Yeah? So the only thing that changes between the code before and now is that we have this weak message. So, however, engineer did not know that this may cause my object to be alive for eternity and never be collected and see his friends die and create out of memory errors on the land of objects to torment the rest of the objects. Yeah. So where is this story coming from? So I will show you some object graphs. So this is a typical, really simplified graph in Pharo. So we have a morph. The morph is a graphic element, and usually in Pharo, if you have a morph that is rising events, he will have an announcer. Yeah, and this announcer will call the registrations to the guys that he will have to notify. So for example, he will have different subscriptions to it, and in particular, as we saw before, we have two kinds of registrations, two kinds of subscriptions. We have strong and weak subscriptions. Yeah. So when we have this kind of graph, actually, we have a morph. We register two events to the morph, to the announcer of the morph. Then we create two different subscriptions. So if I show you this graph, does this one leak or it does not leak? So the answer is it doesn't leak. Why? Because there are no root objects. I don't know if you see it, but there are no root objects pointing to this graph. So there are no memory leaks in here. Now a second case, a more interesting one. So we have a root object which is the weak registry. So this weak registry will hold two weak subscriptions inside the registry. So this guy is the guy in charge of finalization, of sending finalized objects. And then we have the same as before, almost. We have a morph that has an announcer, and in the announcer we have now two weak subscriptions. So these weak subscriptions will have weak references to the morph instead of strong references. So does this one leak or not? No, it doesn't. So this one works, okay? So the question actually happens in the third. This is another, when we mix the two kind of announcements. So I can explain afterwards why the second one doesn't leak, but it's fairly easy. But this one is really interesting. It's a case that we found while debugging code and we're looking for a really strange memory leak, because actually this is the simplified case. When we saw it in reality, it was much complex because we had an object that pointed to object, to object, to objects, and we arrived to something like that. So in here what we have is a weak registry that is the root, and this weak registry is in here because in the morph has two kinds of events. So we are registering strong subscriptions and weak subscriptions. So the question is, does this case leak or not?
Yes.
Yeah. Yes. So why? Because imagine that the garbage collector ignores all the weak references. Now we can find actually a strong path from a root to the object that is the morph. So actually then, since the weak announcer will actually go away, the weak subscription will go away when the morph goes away. And since the morph never goes away because the strong subscription is there, so the weak announcer, the weak subscription is never released. It's a complex example. We try to simplify it a lot to show it, but it's a really strange case where when you are using weak references, you are actually creating the memory leak. And so that was a fun case. So this leaks. Yes. The autopsy that we did from these cases is that, okay, weak references, they do not simply avoid memory leaks. That's not true. So if somebody was using them trying to say, yeah, I am avoiding memory leaks, try to be a bit careful with that. And then also finalization itself can create leaks. Yes?
Can't we use proof on that model that weak announcement subscription holds weak reference to the announcement?
Wait until the next slide.
Oh, okay.
We are, so actually I can even simplify this model more to show why it leaks. So actually this leaks before, because if you see actually the one before here, I actually was going to stand up on the chair. How do you point with this? This? No, I don't understand. Eh? There is no red button. But there are 4 buttons. There's 4 or 6 buttons. Okay, so the thing is that we have this guy, This guy has a weak reference to the morph, and it has a strong reference to this guy. Yeah. So actually, what the weak registry will say is this: if this guy is collected, then I will send finalize to this guy. Yeah. Since this guy is never collected, this guy never receives finalize. Yeah. So actually, what happens in the general case, if you have a weak object in the registry that has a strong part that arrives to its key, to its weak part, then actually what happens is that we have a cycle. We have a path that goes from here, to the guy that is in the weak part. So actually the registration is holding its own weak reference strongly. So that is the general case. And we want to avoid it. We will talk a bit in a couple of minutes about that. So, it's freeze. Okay, so I will let you with Pavel that will explain you how, if you have these problems, what do we do about it? How do we detect leaks? How do we manage it?
So, firstly, how do we detect leaks? Here I've got a set message for you. We do not have any general tool that will help us detect memory leaks. You simply need to test it because memory leaks mostly appears in the application side, in your application logic. So you as an application developer, you should know what to do. For example, if you are creating a tool, you should test your memory leaks the way that you open the tool, do something, close it, and then check if the memory, if the object memory contains something what it should not contain. Some obsolete reference or obsolete instance of your tool, for example. So, sadly, we have no way how to detect them, but as soon as we detect them, for example, in this case, we've got a GT inspector in empty image with only playground opened, and we want to see why there is a one GT inspector instance in this image when we have no GT inspector window opened. So in this case we have several options. Even now we have a simple message that we can send to to objects that is named pointers2, and you maybe know that message. Who knows that? Okay. This message returns set of objects that are pointing to object that you are investigating. So backward references. And the implementation of this message is very inefficient. You can see this is part of the implementation, a little bit simplified. That you, for every such message, traverse all object memory and investigate if the object is pointing to the object you want. And before it does garbage collection, so it takes a lot of time to process one such message. And it's also easy to get lost because you often do not want to investigate only one single reference. You need some traverse the object graph to find what's wrong, and sometimes you need to write such queue of such list of messages to really see what's happening. And if you see that when we were investigating memory leaks, when we were creating Pharo kernel, this is the way we used from command line very often. You, as a standard Pharo user, can use tools. If you click in your inspector with right mouse button, you can choose option menu, open pointers2, and in fact, it has the same implementation. It uses pointers2 message. But it's usable only for very simple cases, and the main reason is because it also creates references from tools to objects you are investigating. If you use this approach, if you do not store results, you have no memory leaks, but here you have new references from tools and you will simply get lost completely. So, what to do in case that we have some references held that Gishe was describing? You will simply see that you are out of possibilities and you need to create your own tool. Tudor will be happy. We try to visualize such object diagrams, and we have seen that it doesn't help us a lot because the object diagrams were really complex and it was hard to find information we wanted. So we needed to create something more simple, more powerful, and we created a tool named RefsHunter. RefsHunter is extremely easy. It creates a temporary snapshot of object memory, simply some array with all objects in your memory, and then it investigates the backward references between objects and stores that. And this snapshot, including such references collection, takes about 40 times the time that is required for one pointers to message. So, if you want only a single reference, it doesn't make sense to make such snapshot, but for more hard cases, it makes sense. And it's really important that it's almost static. You will create object memory snapshot for once, and then you can ask very simply, and you do not need to create it every time you need to find some backward reference. So, the purpose of RefsHunter is one, the single one. It tries to find reference paths from one object to another object. And in most cases, you will try to find paths from your object to some object that is in global space, that is referenced by special objects array.
A root object?
That is root object of your image. But you can use also investigation between two separate objects. It doesn't matter what you will choose. And such queries will be very fast. And you can repeat them, so you do not need to traverse everything back and back and again. So, as I said, it finds reference paths to global space, and it's quite easy to use because it has only one useful message, and it has no GUI. It's not fancy tool that you would use, but it's also very memory inefficient because if you create the snapshot, of course, the snapshot of your object memory is in your object memory. So if you will do that again, the second snapshot will contain original object memory plus your snapshot. So it's not a good idea to make two snapshots from one memory. But as I said, you may use several questions on the one snapshot, and you can download simply from catalog. So in our case of Entity Inspector, you will see that our message way to from returns an array of objects that are pointing to your object from some global space. It still continues, but a hand more here is first object that is global. And as you see, it's 27 objects. So if you would do that with pointers to, and also this is the shortest path. So if you would like to investigate, you will spend a lot of time and maybe you will fail. With this tool, we were able to find a reason why our memory leak appeared, quite easily. So let's talk how to avoid memory leaks. You need to test them and again test them. And for Pharo 6 we already do that. I cannot say that we do that completely, but at least for the basic tools, check if they can produce memory leaks. We have CI job for that that is running and currently green. Maybe it will change in the future. And it's not a good idea, especially for Pharo, to use it as a standard test. Because, for example, if you open a Nautilus, it takes 30 seconds to be this instance of Nautilus garbage collected. That's because some subscriptions to jobs and so on. So if in case you would use it as a standard test, you would need to wait 30 seconds. So if you want to test your project very fastly, you need to wait. So it's not a good idea. That's why we have a special CI job for testing of memory leaks. And the second option, how to avoid memory leaks, is to use Ephemerons finalization. Who of you knows what is Ephemeron? Oh, well. We firstly need to say that Pharo, we haven't invested in wide. We are no authors of Ephemerons. It's old concept and some small talk implementations already have it. But Ephemerons are special objects used for finalization. And as end user, as a programmer, you should know that it can avoid a lot of memories because Ephemeron is an object, so associations that has key and value, and if you've got traverse reference from value or direct reference from value to key, it will be still garbage collected. If that would happen with weak registry, it would be not garbage collected and you will reach memory leak. And you also should know that we already have support for Ephemerons in our virtual machine, and we will soon integrate some image code that will use it. It partly is already integrated, but not active. So, in our case, actually this slide is not very well for this, but instead of weak registry, we will in future use Ephemeron registry, and if this weak registry subscription will be Ephemeron, then after garbage collection of this path, no leak will appear. That's because Ephemeron will have possibility to unsubscribe yourself from the registry, and all this object graph will disappear. As I said, this slide is not very well for the description of it, so let's skip it. So, lessons we have learned. We have learned that announcements are sometimes overused in a very strange way, because some people have troubles to understand it well, and it is overused. We had also very crazy leaking objects in our image. For example, when you open a Pharo 4 image, at the beginning you will have in your object memory, not on your desktop, but in your object memory you will have some instances of dialogues. And that's because such instances were referenced from active hand click status. But that was no real everlasting memory leak, because every time you move your mouse and click somewhere, the click status changed, and this memory leak disappeared because the garbage collector destroyed the dialog instance. As I said, not every leak lasts forever. For example, for the Nautilus, it takes 30 seconds to be garbage collected. It's a lot, but it's that. And we also learned that we need better tools, and that if we have some problems, it's often a good idea to create tools that will help to solve it.
How about, do you mean that within 30 seconds the garbage will have been collected, or do you mean that you have
Because there is some job some delay that takes 30 seconds, and after the 30 seconds the reference will be, pointing object will be garbage collected, so also the Nautilus will be garbage collected. So it's not a good idea to open hundreds of